Hello, Accelerated Chemistry students. This is Ms. Crisafoli, and this is your Chapter 10, Section 1 video notes all over the mole, which is a measurement of matter. So let's talk about measuring matter. Chemistry is a quantitative science. Quantitative, remember from way back when at the beginning of the year, means that you have to have a quantity or a number. This means that you will analyze matter and perform calculations that relate different compounds in a chemical reaction. So to solve these problems, you will need to be able to convert different units. This is going to bring back all of the skills that we talked about in Chapter 3 way at the beginning of the year. So if you want to pause and go back and look at that, I suggest that you do before you continue with your notes. So let's do a review of dimensional analysis. So what is the mass of 90 averaged sized apples if 1 dozen of apples has a mass of 2.0 kilograms? All right, we're going to have to set this up using dimensional analysis. So let's analyze. Let's list the knowns and unknowns. So we're going to use dimensional analysis to convert the units of number of apples to mass of apples. So what do we know? We know the number of apples is 90. We know that 12 apples is a dozen, and we know that a dozen apples is 2.0 kilograms of apples. And what we don't know is what the mass of 90 apples is going to be in kilograms. So we're going to calculate and solve for the unknown, but first we need to identify the sequence of conversions needed to perform the calculation. We need to go from number of apples to dozens of apples to mass of apples. And this is a skill. Preparing and planning out your list of conversions is something that we talked about way back when in Chapter 3, and it's going to come back again in this chapter and for the rest of the year. So we're going to write the conversion factor to convert from number of apples to dozens of apples. So we could have 1 dozen apples is 12 apples. And then we're going to write the conversion to convert from dozens of apples to mass of apples. And then we have 2.0 kilograms of apples to 1 dozen apples. Now we're going to multiply the number of apples by these two conversion factors to get the answer in kilograms. So we're going to start off with 90 apples. We're going to multiply that by a dozen apples is 12 apples. And then we're going to multiply that by 2 kilograms of apples is 1 dozen apples. And as always, before we even plug anything into our calculator, let's check to make sure all of our units cancel, and they do. And what we want is kilograms of apples, and that's what the whole problem is asking us to solve for. And that would be 15 kilograms of apples. Once you multiply 90 times 1 times 2.0, divide by 12, divide by 1, you get 15. Now, the unit apples and dozen apples cancels, so the answer has a unit of kilograms. And remember, all of these problems that we're going to have are going to have to go back to be reported to the right number of significant figures and also to the right unit. So now we have to evaluate. A lot of times when you're going to be doing these problems, you're just going to want to get to an answer. But in chemistry, you need to know what your answer means, and you also need to make sure that your answer makes sense. So a dozen apples has a mass of 2 kilograms, and 90 apples is less than 10 dozen apples, so the mass should be less than 20. And it is, so that makes sense. So now let's talk about what is a mole. Recall that matter is composed of atoms, molecules, and ions. These particles are much, much smaller than grains of sand, and there are a large number of them in a sample of a substance. So let's relate moles to eggs, more specifically, a dozen eggs. So when you're counting eggs, it's easier to group them and to say how many dozens you have. You have 3 dozens. That means that you have 36 eggs. You have 5 dozens. That means you have 60 eggs. So a dozen is a specified number of things, and more specifically, it's 12 things. So when we count with moles, we use, as chemists, the unit called the mole. A mole is a substance It is 6.022 times 10 to the 23rd representative particles of that substance, and it is the SI unit for the measuring the amount of a substance for chemistry. The number of representative particles is a mole, is 6.022 times 20 to the 23rd, and that's also known as Avogadro's number. So you'll hear me go back and forth between saying it's a mole of anything is 6.022 times 10 to the 23rd, or it's Avogadro number of things. So the term representative particle refers to whatever species is present in the substance. So what are we talking about? Are we talking about atoms? Are we talking about molecules? Are we talking about formula units? So the representative particle of most elements is the atom. And remember, there are 7 elements that are normally exist as diatomic molecules: H2, N2, O2, F2, Cl2, Br2, and I2. The representative particle of these elements are all molecular compounds is a molecule. The molecular compound of water and sulfur dioxide are composed of H2O and SO2 molecules each. So, and then also for ionic compounds such as calcium chloride, the representative particle is a formula unit. So remember, molecular compounds have molecules, diatomic elements are molecules, and ionic compounds have formula units. So the relationship 1 mole equals 6.022 times 10 to the 23rd representative particles is the basis for the following conversion factors that you can use to convert number of representative particles to moles and moles to number of representative particles. What does that mean in a nutshell? Basically, you get 2 conversion factors. You can write 1 mole over 6.02 times 10 to the 23rd representative particles. Now remember, that could be atoms, molecules, ions, formula units, or you can write it as the reciprocal, where 6.022 times 10 to the 23rd is on the top. Again, representative particles, molecules, ions, formula units, atoms. So let's do a sample problem. Let's convert the number of atoms to moles. So magnesium is a light metal used in the manufacture of aircraft, automobile wheels, and tools. So how many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? So again, we're going to go step by step so that we get really used to this. I want to make sure that you write this down in your notebook. So first, we're going to list our knowns and unknowns. We need to make sure that we understand what the conversion is first, though. What are we going from and to, so we know what conversion factors we need? So we're going from atoms to moles. So we know that the number of atoms given in the problem is 1.25 times 10 to the 25th atoms of magnesium. And then we don't know how many moles that is. So we need to figure out what is the relationship between moles and the number of representative particles, or atoms in this case. That's 1 mole of magnesium has 6.022 times 10 to the 23rd atoms of magnesium. That's that special number that you better have memorized by the end of this chapter. So we're going to solve for the unknown. So we're going to write the conversion factor so that you can get the right version of it to put it into your dimensional analysis correctly. So we can write 1 mole of Mg over 6.022 times 10 to the 23rd atoms of Mg, or we can write 6.022 times 10 to the 23rd atoms of Mg over 1 mole of Mg. We want the top one though, because we're starting off with atoms and we want to go to moles. So let's look at how we set this up. So we're going to write the conversion factors you get based in this relationship. So 1.25 times 10 to the 23rd atoms of Mg is going to be multiplied by 1 mole of Mg over 6.022 times 10 to the 23rd atoms of Mg. And when we cancel those things out, we are set up correctly and we get 0.2808 moles of Mg. Now, the number that we started off with had 1.25, which is 3 sig figs, so your answer has to have 3 sig figs. Remember, your conversion factors are never used to determine the correct number of significant figures in your answer. And then we're going to have to, again, make sure this makes sense. So the number of atoms that we were given is about 1/4 of Avogadro's number, so we should have less than 1/4 of the moles of atoms, and we do. And then also, since the number that we were starting with has 3 sig figs, our answer also has to have 3 sig figs in it. We're just going to keep trucking along. Now, what happens when we convert between the number of particles and moles? So suppose you want to determine how many atoms are in a mole of a compound. You will do the same exact thing, and you would look at it based on the chemical formula. This number is going to be determined on what the chemical formula is. So the number of marbles in a dozen cups is 6 times 12, because look at our cups on the right. We have 6 marbles in each cup, or 72 marbles. So a mole of molecules contains more than a mole of atoms. Makes sense. So to find the number of atoms in a given number of moles of a compound, you must first determine the number of representative particles. So you're going to look at how many elements are in the compound, or how many atoms are in the compound, and then you're going to have to use that 6.022 times 10 to the 23rd representative particles in 1 mole to determine your answer. So let's convert from moles to number of atoms. So propane is a gas used for cooking and heating. How many atoms are in 2.12 moles of propane, which has a formula of C3H8? All right, here we go. We're going to list our knowns and unknowns. First, we have to map out our desired conversion. So we got to go from moles to molecules to atoms. So we know the number of moles is equal to 2.12 moles, which is C3H8, which is propane. We know 1 mole has that many molecules in it, and we know that 1 molecule has that many atoms in it because we have 3 carbons, 8 hydrogens, so that's 11 atoms. What do we don't know? We don't know the number of atoms that is. All right, so let's figure out what the conversions are. So we're going to have to use this one. 6.02 times 10 to the 23rd molecules is in 1 mole. And we got to remember to write this and flip this in the right orientation so that we have things that cancel. And then the second conversion we're going to need is that we have 11 atoms in 1 molecule of C3H8. How do we get 11? Remember, we have 3 carbons and 8 hydrogens in 1 molecule of propane. That's how we got 11 atoms. So now let's set this bad boy up. So 2.12 moles of C3H8 times 6.022 times 10 to the 23rd molecules over 1 mole times, we have 11 atoms in 1 molecule of that. We're not touching our calculator yet. You better not touch it. You got to make sure your units cancel. Oh my goodness, they do. So now we can touch our calculator. 2.12 times 6.022 second E23 times 11. That gives us an answer of 1.40 times 10 to the 23rd atoms. All right, does that make sense? It does. There are 11 atoms in each molecule of propane and more than 2 moles of propane. So the answer should be more than 20 times Avogadro's number, and it is. And the answer has 3 significant figures because the number we started off with had 3 significant figures in it. Pretty self-explanatory. We're going to get more and more practice with these problems over the next couple of days. So if you're like, what is going on? Have no fear. There's a method to my madness. Remember, let's talk about molar mass. The mass of a mole of an element. The atomic mass of the element is expressed in grams, is the mass of a mole of the element. The mass of a mole of an element is its molar mass. For example, if you were to look on your periodic table, now pause the video, get that yellow periodic table. I don't care if it's downstairs in your book bag. We need it. Look where carbon is. It's number 6 on the periodic table. That number underneath your element symbol is the molar mass. It's 12.01 grams per mole. Now look at hydrogens, number 1. Top left corner, group 1. Underneath that H symbol, it says 1.008 grams per mole. That's the molar mass of hydrogen. So, how many atoms are contained in the molar mass of an element? So, the molar mass of an element has 6.022 times 10 to the 23rd atoms of that element. So the mole can now be further defined as the amount of a substance that contains the same number of representative particles as the number of atoms in 12 grams of carbon-12. So how do we calculate the molar mass of a compound, or the mass of a mole of a compound? First, you're going to count the atoms in the compound. Then you're going to look up the mass of each element on the periodic table in the compound. Then you're going to multiply the mass of the element by the number of atoms of each element. Then you're going to add them all up. This is the easiest thing that we're going to do. So let's do an example. As always, let's find the molar mass of a compound. And the compound we're going to find the molar mass of is H2O2. What's the molar mass of hydrogen peroxide? Okay, so let's list what we have. We need our periodic table, so you better have that out still. Get your calculator ready. So first thing we need to do is we need to figure out how many elements we have and what is the mass of each element that we have. So the molecular formula is H2O2. The mass of H is 1.008 grams per mole, and the mass of O is 16.00 grams per mole. And what do we not know? We don't know the molar mass of this compound, so let's figure this out. So we're going to multiply the number of each element by the mass of each element, and then we're going to total them up. So here's our formula one more time. We have H. There's two of them, so we're going to take 2 times 1.008. And we have oxygen, and there's 2 of those, and each of them is 16.00. So once we do 2.1008 and 2 times 16.00, we're going to add everything up, and we get 34.016 grams per mole. All right, does that make sense? Well, if you were to look at it very specifically, the mass of hydrogen and the mass of oxygen is about 17.008. And we are taking double that because it's H2O2. So it does make sense that your molar mass would be 34.016. That makes 100% sense. Now, here's the thing I want you to remember. Do not round your molar mass. Write it down, all of the digits off the periodic table, and you're not going to round your final answer either. Why are we doing this? Because what is coming in the chapters to come, we need very precise answers. So no rounding. Okay? We're going to practice all of this that we talked about in class tomorrow. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the Textbook Resources CD and pearsonchem.com. Thank you so much. Have a great night.